very excited to present this work. It's the result of a wonderful internship with Edouard Gorbunov, who was intern at the time and now is doing a postdoc with me. And yeah, we kind of, as you will see, like I think it's very exciting for two aspects. Like the results, in my opinion, are exciting for themselves, as you know, like for the contribution, like the theoretical contributions. But what's even more interesting and what I think should interest you even more is like actually how we got this result, and like it's the proof techniques we used, and more especially the fact that we use like computer-assisted proofs. And you will see it's very interesting. So yeah, as a short summary, what we do is, I don't know if you're like familiar with the extragradient methods and what's called extrapolation from the past. If not, it's okay. I'm going to explain everything to you today. But what we managed to prove is so some convergence rates. So in the context of variational inequality problems, and more especially like 1/k last-iterate convergence rate. And like the crux here is the last-iterate aspect, which was an open question since basically the introduction of these algorithms. So in like 1976, respectively, and 1980. And so what's very interesting, and really what I want to share with you today, is how we got the proof, the tool we use, and yeah, like basically the proof is obtained via some like very cute semi-definite programming that gave us hints on how to actually formally prove this result. So yeah, the outline of the talk today is going to be fourfold. So I'm going to have short motivations. I apologize for the beamer slides. You know, there is not going to be that many animations and images. Usually, I think it's nice to have like images to illustrate the motivations. But as you will see later, it's nice to have beamer for like the section 3 and 4. So I'm losing a bit for the first section, but like section 3 and 4 will be great with beamer.
Can I just interrupt you a second, Gauthier?
Yes,
I think the screen sharing is not working.
Okay, that's very important. Yes, it's okay. Anyway, I was.
Okay, perfect. Now, okay,
yeah,
that's
it should
perfect.
work now.
Perfect.
So yeah, you missed nothing. So don't worry. It was just this outline. So cool. So basically, the motivation for this work are variational inequality problems that actually are introduced later. So in a variational inequality problem, you want to find a point x star in the constraint set, such that we have this property, which is like basically f of x star inner product with x minus x star is positive for any x. So this one in the constraint. And basically what it's saying, you know, intuitively, is that the vector field f, so f is a vector field, it's the thing you're going to follow. So for instance, you can think about like a gradient vector field. And what it says, this condition is just like the negative gradient or the negative vector field is pointing out of the constraint. So like you're following your gradient, and at some point you hit the constraint and you're stuck and you're at, in the case of gradient descent, the minimum of your function, and in this marginal problem at the optimum of your problem. And so the motivation for this are, I mean, gradient methods, but I mean, gradient methods are very specific, and they have, you know, we can leverage more structure of the problem. But so beyond gradient method gradient descent is like basically traffic equilibrium computations. Actually, you have someone, Patrice Marcotte, who worked a lot on variational inequalities here at Nero. And that he wrote a nice review paper about variational inequalities, where he explains that, yeah, traffic equilibrium computation, so I think it's some sort of equilibrium, it's not Nash, it's, I forgot the name, but... Correlated? No, it's not correlated, it's something...
Yeah, no, sorry.
No, so yeah, it's I forgot, yeah, another name, sorry about that. But you have this equilibrium problem computation that are not min-max problem. And you also have like min-max problems. So it's motivated by originally economics. And like, so in min-max is like basically the Nash equilibrium of the zero-sum two-player game. And yeah, so it really was like big during like 60s, 80s, when like there was a lot of application in economics, and more recently, it got back to the spotlight because of the modern machine learning application. So basically, adversarial training and generative adversarial networks, for instance, can be formulated as a min-max problem, where U and V will be not always, but often U and V are the parameters of your neural networks. And you have a competition between these two neural networks in specific games. And so it ends up being a min-max problem. And so trying to find the methods to find the Nash equilibrium of this game by using the gradient of f with respect to U and V. It's actually very important in order to kind of find efficient method to train generative adversarial network or adversarially robust classifier. Any question about everything so far? I hope it's clear. I hope you're excited about the motivations. I am. So yeah, basically that's why we want to solve this problem, because basically I think I'm going to illustrate later, but finding this guy is basically equivalent to find the min-max of, at least the local min-max. So if f is convex concave, finding the solution is equivalent to find the min-max of the problem. And the assumptions we're going to make on the vector field are like two very standard assumptions, which is that the vector field is Lipschitz. So it's just like a regularity assumption. Basically, we want the vector field not to be too crazy. So if the x and y are closed, basically f of x and f of y should be closed. So it's just Lipschitz continuity. Everything is, I think, familiar with this. And the second assumption, which is slightly more, maybe you're all very familiar with variational inequalities, and I can move on. I don't know. But okay, if not, I'm gonna, that's good like this. So F monotone, it's basically the generalization of convexity. So if F is the gradient of a function, and this function is convex, this inequality is true. And this is kind of the generalization. And basically what it says is that your vector field is like minus your vector field is pointing toward the optimum. Okay? So just like, in convex minimization, you can get, by following the gradient, you get closer and closer to the optimum. Here it's a bit a similar assumptions that says that by following this vector field, you will get kind of closer. So yeah, that's the idea. And for instance, if you have a min-max problem and f is convex concave, it's actually equivalent to find the solution, the min-max, or to find like a pair of points, u star and v star, such that this condition holds. It's just like basically the first order stationary condition that is necessary and sufficient when you have convex concave form. So it's basically equivalent to the variational inequality problem if you realize that basically uv is your variable x, and your vector field is the gradient for the descent part and minus the gradient for the ascent part. And so the concatenation of these two gradients, this gradient and this gradient is not a gradient anymore. And so this vector field is way, in some sense, less well behaved than a single gradient. And so, for instance, we will see that if you just follow the vector field, you just apply the extension of gradient descent. So you just do compute f and do like equivalent of a gradient step. Actually, it can fail. And so this is why I'm going to present like the extragradient methods that are the principled way to solve these problems. So in particular, I'm going to make a simplification here. It's nice. It's going to be easier for us. So no more constraints. So we're going to take the constraints at Q. So if you remember, like we had this for all X and Q. But if Q is everyone, it means that basically this inner product must be positive in any direction, which means that basically F must be 0. So that's nice.
Q, you mean just Asha?
No. So Q here, Q is the set of constraints. Maybe it's a bad name. Okay. So Q is really like including in RD. Okay. Anyway, the good thing is we can forget about Q because Q is RD now. So this is RD, and the new problem is nicer. We just want to find a point where the vector field is 0. So in gradient descent, we want to find a point where there is 0 gradient. And more generally, we just want to find a stationary. Cool. And so, as I was saying, the naive approach is to generalize gradient descent. So you'd have your iterate, your past iterate. You compute the vector field at this point. You do it's not really a gradient step. I mean, it's the same idea. You do a step, and you get your new iterates, and you do this iterator. So it seems very natural, and for minimization, we know gradient descent is nice. It's like we know how it converges in lots of cases. But actually, for games, so like for min-max problems, for anything that is kind of beyond minimization, it fails. And there is a very simple example. Basically, you take this vector field that is exactly rotating around the optimum. So, you know, like this is the optimum, this is the vector field, and it's actually perfectly perpendicular to the direction to the optimum. Actually, it corresponds to the monotonicity condition where it's 0. You know, the larger or equal to 0 is always equal to 0 for this one. And you're screwed because you have your optimum, you follow the vector field, you actually follow the tangent direction to the right direction, and you actually rotate around without converging. And actually, you slightly diverge. So, like in yellow, you have the gradient method, and you see that it turns around the optimum without never ever converging. And so that's why you know it's not it's nothing new. Right? It's from the 60s, 70s. People in like so it was really in the context of more OR and like traffic equilibrium computation, like they came up with, and economics actually. Extragradient method was introduced by Korpelevich in 1976, and she wrote that she got inspired by some extrapolation ideas in the context of, I think, market equilibrium computation. So it was for this kind of equilibrium computation. And so the idea is basically, I'm going to present also like the optimistic gradient method. And basically, it doesn't look obvious from here, but these two methods are very similar. And I'm going to describe the intuition for extragradient because I'm going to focus on extragradient today. So it's really, it looks like it has a flavor of like the gradient method. But the trick is instead of taking the vector field at the point xk, you take the vector field at xk minus gamma f of xk. So in some sense, what you do is you do a step like this guy, you do a gradient set to compute this guy, which is kind of looking at the future. You kind of like looking at what's going to be the future if I were to do a gradient step. And then I compute the vector field at this future point. And that's really, it gives basically, it gets a bit the information of the curvature of the vector field. And basically, for instance, in that case, you would be at a point like, let's say, the black point. You do a gradient step, you end up at this point. It is there, and you see that basically you get a similar vector, but now that it's slightly rotated toward the center. And you end up having, instead of having the pure rotation around the optimum, you end up having this like purple trajectory that are rotating still, but also got the information of the curvature of the vector field, and so get slightly closer and closer to the optimum. So I mean, this can be formally proved. And that's kind of like the goal of this work today, to really understand well this method. I mean, and to bring new contributions.
But we still have the condition of Lipschitz.
Of course. Like all the proofs are done under monotonicity and Lipschitzness. Otherwise, actually, there is impossibility results. If you don't assume F to be monotone, so it can be arbitrary and arbitrary vector field, you can show that there exists some vector field where any reasonable methods will never converge.
So basically, you have a Lipschitz and monotone.
Yeah.
Okay.
Yeah. So yeah, we will focus on this one. Optimistic gradient can be, you can really basically see these two methods if you do like a Taylor expansion, for instance, as a gradient method plus a corrective term that depends on the second order information of the vector field. and that is pushing you toward the optimum. So, and yeah, what we want to show, the convergence criteria is the norm of the vector field. So, of course, because this is the optimum. Like we are at the optimum when the vector field is 0. So the convergence criteria is like we want to make the norm of the vector field as small as possible. And so, okay, what is the why am I doing all this parallel with the minimization case? Is because in the minimization case, we have gradient descent, and we know that when we minimize a convex and smooth function, which is exactly, the gradient of the function is monotone and Lipschitz, we know that we can iterate on our methods, and we know that we have some guarantees. We know that like the suboptimality, so the value of the function at xk minus the best value you can get, the global minimum, is smaller than 1/. So we have a specific convergence rate that's reasonable, reasonably fast, and we are happy. And more especially, what we have is that the last iterate is the best. The xk, the last one that we have computed, and it's very natural, is the best one. It's the closest one to the solution. And it makes sense. You do gradient descent, you get closer and closer. There is no reason not to keep the last one. And why is it very important? It's very important because in machine learning, when we do, for instance, non-convex minimization, we cannot guarantee such things. But in non-convex minimization, things, close to the global minima, for instance, this is locally convex. It looks like a small ball. And so we want, basically, once we get into this locally convex area, we want this property to be true. We want basically the iterate to stay close and to get closer and closer to the global minimum. Even if we cannot guarantee, far away because of some madness that we will get very quickly in this local area, we want that in the local area where it's nice, we want this property. And the question is it seems natural, can we prove a similar statement for VIPs with HEG? So it's the same assumption in some sense, generalization of the assumptions. We get the algorithms that is supposed to be the nice one. Can we prove a similar statement? And so basically the equivalent hypothesis, as I was saying, is F monotone and L Lipschitz. And if we look at the literature, there is a lot of work since basically Popov and Korpelevich. More especially, people in optimization started to be very interested about convergence rates during the 2000s. So that's why the rates are a bit after the original papers. But yeah, big names of optimization. So if you know optimization, you probably know its names like Nemorsky and Nesterov. They worked on this algorithm. They worked on each, and what they managed to show is that basically you have a 1/k convergence rate for the gap, which is something that is actually, I don't want to define it, but it's a criteria of convergence, similar to the norm of the operator. But what's very interesting and unsatisfactory in some sense is that it's not the last iterate, it's the average iterate. So you have to compute your algorithm, and then when you want to stop, you stop. You use all the iterates you had in memory, you average them, and this is only this guy that will be actually the one that has guarantee. And why it's not satisfying is because intuitively the initialization, for instance, is supposed to be very far from the optimum, while the last iterate is supposed to be way closer. So you don't want to use the initialization in your average. You want to use only the last, maybe the penultimate iterates, but you don't want to do this average because it seems that you are losing something. Any question about that? Okay, cool. And so yes.
So this is how they used to give some guarantee.
The proofs were always on the average,
okay,
or on basically the minimum iterate, which is a trick. So when you have a result on the average, often you can get a result on the minimum, but you don't know, basically it's a bit, once again, unsatisfactory because we don't know who this guy is. The K that achieves this minimum could be 1 or like k over 2 or whatever. And so once again, we have this like unsatisfactory feeling that the last one should be the best, and we are not able to understand this method well enough to prove it. And yeah, I mean, there is similar results for OGID, which has been slightly less studied, but yeah, no result for the last-iterate. And actually, what's very nice for us is that these people, ici et al., they explicitly stated the last-iterate convergence rates for these algorithms as an open question that they were not able to solve. I'm gonna get to the proof, I promise, but I need to give you the context of why it's interesting. So yeah, there is people who prove that basically one cannot do better than this. So it's a lower bound, it's a sigma, it's a omega, sorry. So we cannot do better than this, and so with the last-iterate, yeah, we want to prove like the upper bound, so the other side of the thing, to show that it's actually this lower bound is achievable. And they basically are able to prove the upper bound like recently, like 2 years ago, but by assuming like some more things. So they assume that now the Jacobian of the vector field, so like this like big matrix that would be the Hessian in the case of minimization, has some Lipschitz property. And they are able to prove it with a very complicated, like 20 pages proof. And interestingly, they conjecture that these additional assumptions was necessary, like to prove the proof. So it really shows that, like, you know, smart people tried, and it was not trivial. And like, I think we succeeded in proving this because we really took like this like alternative ways. As you will see, like this is like, I mean, I'm still mind blown by the techniques, honestly. So basically what we managed to show is that their conjecture was actually incorrect, and that we can show the last-iterate without additional assumptions and with a relatively simple and interpretable a posteriori, once everything is clean. Yes.
Sorry, the just thing as you explained. Can I ask you something about the previous slide?
Yes.
About the so since the proof is on the average of all of the points, is it the case with these techniques that sometimes you find a good point and then the next point is worse?
Yes.
Right. Okay.
So I mean, so yes and no. These guarantees cannot guarantee better than exactly what you described, and actually some methods behave like that. So like for instance, in convex minimization, there is like a Nesterov basically grand descent with some sort of momentum has some behavior that does something like this. And you really like, this is the time step t, and this is the convergence criteria like suboptimality, and you get really good, but then you have a really like a kind of like in the following step you stop to improve drastically. So these kind of proofs cannot discriminate between this and more like nice something. But because we proved that the last-iterate was converging on the same algorithm, these results were not representative of what was happening in practice. Cool. So we have all this, and we have the last-iterate convergence, and like what's very exciting is like we derive the results via solving basically what's called performance estimation problems numerically. So we basically, long story short, we leverage some numerical tools to give us direct hints on the proof, like on like how to prove, like how to combine inequalities. And I'm going to spend basically, as you can see the number of dots here, the rest of the talk trying to give you insights about this. So, and I think, that's why I wanted to spend some time on the motivations, because I think like this tool was a complete game changer for like just trying to prove stuff in this context of like convergence of algorithms. So yeah, basically it's a very powerful technique that I will like detail, and it has been introduced decades, I mean, almost a decade ago now. And I mean, yeah, there is a lot of work around it. And it's a tool, so like it's about like all these works are about like either understanding this tool better or about leveraging this tool for some new exciting methods. And if you, at the end of the talk, are very excited about this, you can check this wonderful website by Adrian Taylor, who really introduced this tool very well, and he has a blog post about it, where he really gives some similar intuitions as what I'm going to give you, but on other examples and so on. So yeah, I really strongly advise you to check it out. Cool. So basically, what is PEP? So PEP is applied to a method M, so an algorithm. So you can think about like gradient descent. I'm going to have a concrete example later, but any optimization methods. You fix the optimization methods, and what you want to do is you want to prove that it converges. You want to prove some properties, and you want to prove some properties on basically a class of problem P. So the class of problem is like, oh, I want to show that my method gradient descent converge at this specific rate on convex and Lipschitz functions. So if you don't ask for the function to be Lipschitz or convex, you cannot prove anything. So the class of problems is kind of the restriction of functions or vector fields in this case that you allow your algorithm to work on. And so in some sense, when you think about proving a result, what you want to do is that you want to find the worst case problem. So like, okay, what is the worst case for my convergence criterion? So, for instance, norm of the vector field here of the last iterate, such that my problem is in my class of problems. My initialization is whatever. And basically xk is the output of M after k iteration. So basically xk has been computed from x0 after k iteration. And basically, what is very important here is the problem. So this is the general framework. I think it's very important to have a concrete example. This is simpler. So what we want to do is like trying the worst problem. So what in the worst case I could obtain from the norm of my operator. So knowing that f has to be monotone and Lipschitz, x0 is initialized, I'm just putting x0, I'm just normalizing my problem because otherwise, my initialization could be arbitrarily far and I would be screwed. So I'm just asking for normalized initialization, not too far from the optimum. And what I'm saying is just f has constraints, so it has to be monotone and Lipschitz. And xk is like iteratively computed with this method. So I'm start with x0. You think about it, like x0 is a variable I'm actually not setting. Like x0 is an unknown variable in this problem. We just know x star is fixed. Let's fix x star at the origin. So I want to find the worst initialization and the worst vector field that is monotone and Lipschitz, such that when I'm going to compute my iterate, the last one is going to be like maximum. And so when you think about it, if you're able to have, like, when you prove a result, what you are saying is like, you are saying that this norm, for instance, is smaller than a specific quantity for all monotone and Lipschitz problems. So what you're exactly saying is that this max is smaller than a specific quantity. And so what I'm doing right now is just like rewriting this kind of conceptual idea of the proof into something that will very soon look like a semi-definite program. And then the idea will be to use then like computational tool to look for the hardest function, the hardest monotone vector field against your algorithm. And it gives like direct hint about the proof, because once you know the hardest problem, you kind of know what is the best you can do. Does it make sense? Yeah. Hopefully. But so yeah, you can basically argue with me, but Gauthier comment, like this space is infinite dimensional. I cannot optimize over all the function, all the vector fields. Like it's not a semi-definite program. And I would be like, yes, that's true. But basically, that's why PEP is, not trivial and very interesting. Is that there is some key ideas, and one of the first key idea is to replace this problem by something finite dimension. And the key element, I can tell you already, what is the key element here is the fact that the monotonicity and the Lipschitzness conditions are, you only need to verify them at the point you visited. You know, the point that the algorithm don't visit, you don't care about them. You just care. And when you think about it, when you prove like a given result, you only use the inequalities of monotonicity and Lipschitz or whatever at the point that are visited by the algorithm. So that's exactly this idea. Like you're gonna only care about like the points that are visited by the algorithm. So you're gonna have a finite number of conditions. It's gonna become like finite dimension. So we introduce new variables. So xk and j of xk, and basically this guy is the variable that defines the potential value that the vector field could have at the point xk. So like because the unknown is f, basically now the new unknown is x of f of xk, so we call it gk. And same for the gk tilde. And so this is just now extragradient reformulated with these new variables. And as you know, here the unknown is f, was f, the vector field, and here the new unknowns are just these like vectors that corresponds to the vector field at this specific point. And so we just get now a finite number of unknown variables. And the constraints are just the constraints for this like xk, gk, for monotonicity and Lipschitz. So it's the same problem. We want to maximize the latest vector field value such that we have this guy that belongs to RD. You have the initialization smaller, relatively close to the initial point. You update everything using what is supposed to be extragradient. So, you know, like this is the extrapolation step. I was telling you, like looking at the future, and then you use the vector field at xk tilde to update your point. And so basically the question is like, we want the existence of f that interpolates, so in the sense like such that f of xk is gk. And more especially, this is the very important thing, this f has to be monotone. So now you have introduced just new variables, and you want f to be like you want to verify the monotonicity and Lipschitz. So I haven't, it's still infinite dimensional, but just the next step is going to be to basically remove this and just add the constraints for the. So yeah, actually necessary conditions of the existence of this operator. So if there exists such an operator, necessary, of course, all the monotonicity and Lipschitz condition are valid for all the pairs. So this is just like saying that this guy is monotone and Lipschitz. So I'm just like trying all the possible combinations with this variable. I'm trying them. So for all the pairs, etc. And so I get this new problem where now I'm not asking f to be Lipschitz and monotone because f has disappeared. I have just the necessary condition that if g tilde and gk was corresponding to a monotone and Lipschitz vector field, we would have to have this for all the pairs. And so the question is like, is it sufficient? You know, can like, if I have, you know, what is the inverse problem? If I have such gk's that verify all these conditions, can I find a f that's gonna correspond to this gk everywhere? The answer is no. So the answer is very interesting and very actually settled. So if you put only one condition, the answer is yes. So only monotonicity or only Lipschitz, it's yes. So the answer is no, but we are in the worst case. So we're just going to be a bit worse than the actual real worst case. So we are losing, we are not perfectly tight. So maybe this guy is going to construct a problem that doesn't exist. But if this guy, this maximization is already close enough to our upper bound, we are good. So we have something that is a bit worse than the real worst case. But if it works, we are on business. So that's really the idea. So now we have this problem. If we are able to solve it, and if we are able to get the rate we want, we are good. Like basically, we don't have a proof yet, but we have a numerical hint that the worst problem against your algorithm cannot break it, and that it has to be true that we have the last-iterate convergence for the process. Yes, so it gives a valid above. Then, yeah, I will see later that can be because it's not exactly SDP yet, but I mean, if you're familiar with SDP, it's around the corner. But let's say we are able to solve this problem using standard libraries and like optimization tools. We can use it. This is what we did in our paper. And so this is just plotting this function as a function of k in red. So 1/k convergence rate. This is like what we would hope to show for our algorithm. And so if we set, because some of the hyperparameters, gamma 2, gamma 1, L, because we have to numerically solve this to a standard value, what PEPS tells us is like the upper bound on the worst problem against extragradient cannot do better than the green field. So basically what PEP is trying to tell us right now is that it's impossible for him to find a problem that breaks that prevents the norm of the vector field to be larger than something whatever. So it's already the hint that like this should be true. Like now I could put this in a paper and say I have a pretty fair evidence to conjecture this result. Like it's already enough to do some very confident conjectures. And the next step is actually I'm gonna show you how we can use this PEP again to basically extract the information about the worst case problem to figure out the proof, the formal proof in the general case. So yeah, forget about this. I explained everything in details. Any question about that?
The green dots, those are experimental numbers.
Yes.
And the green line showing the dots, right? That's not
yes.
the actual rule.
Actually, so it's more than, so there is a dot for each k.
Yeah.
So the green dots are just for people that are colorblind. Yeah, we compute it for all value of k. What is the worst problem? If we stop at the specific k, what would have been the worst problem break to maximize its number?
And this is always an intuition because you have no guarantee of what happens at k equals 100.
I 100% agree. This is why it's not a proof, but I mean it's pretty convincing.
Yeah.
Also, like it's a semi-definite program, so it grows because you can see that the number of constraints it depends on the number of pairs, so it grows quadratically in k. So above 50, it starts to burn your computer. So I mean we can go a bit beyond, but not that far. But yes, that's not a proof for two reasons. The first one is the one you said, because you stop at a specific k. The second one is because you're numerically computing it for a specific value of L, gamma 1, and gamma 2, while you would like to prove it for any configuration. And yeah. But
you still have a little side from
I mean, like, when so yeah, I mean, I can get into why it's actually more interesting than you may think is that there is a lot of convergence criteria you can look at. There is a plethora of things you may want to prove. Like I could think about, oh, this is this guy that converges, or like this guy plus something else, etc. And so you can conjecture what is the right quantity to look at, and then make a conjecture about, I think this quantity is decreasing. You plug it into PEP, and PEP is going to actually tell you if a problem is able to break your conjecture and like prevent your quantity to decrease. So like beyond this plot that is a positive answer, there's all these plots that gave negative answers about like other quantities that we had looked at and that actually were not behaving as well as we wanted. So, and I'm gonna actually, very interestingly, if you look at optimistic gradients or the other alternative quantity, this guy doesn't decrease. And with PEP, you verify this in like 2 minutes. If you wanted to build yourself the counterexample where it doesn't work, it's more a week than 2 minutes. So that's really what's convenient. And actually, the quantity that decreases in the case of optimistic gradients is a bit, it's more convoluted. And really, PEP helped to basically first conjecture which was the right one, and then conjecture came up with it. So yeah, basically, yeah, I'm gonna skip that. How am I doing on time?
It's 10 minutes.
10 minutes, great.
10, 15.
Great. So I'm good. So yeah, as I was saying, like it depends on the parameters and so on. And so what we try to prove, because it seems to be true on this plot, is that this guy is actually monotonically decreasing. So one other illustration of FEP, you can really put not whatever you want, but we have a wide range of hypotheses you can test. In particular, you know, before we wanted to test that the last iterate was small. Here we just want to say that with one step, this guy decreases. So if this maximum is negative or 0, it means that basically the norm of the vector field is decreasing, and we would be happy for some reason. And so I'm gonna explain you, like I'm gonna unroll you this specific example because this is the one that basically it's the simplest one, and that's also the one we actually ended up using for the proof. So we have this, we use PEP. So we end up having this formulation. So the gradient at the first step minus the norm of the vector field at the first step minus the norm of the vector field at the second step. The unknowns are the value of the vector field and the initialization. And we know that the iterates are updated according to extragradient with an extrapolation step and an update step. And we want monotonicity for all the pairs, Lipschitzness for all the pairs. So yeah, it's a bit long to write manually, but it's okay. Here you have only six equations. Okay, cool. Yes, okay, I have it. What is the difference here? Oh, okay, it's the same. I just get this. That's okay. Cool. And so the trick to formulate this as a semi-definite program, if you are used with semi-definite program, you should like this is standard trick. What happens is like everything is linear in basically where the variables are these quantities, basically. So like if you look at the gram, everything is linear in the basically inner product of between the variables. So you consider like this representation where like you have like x0 like all the vectors, and you look at this gram matrix that basically contains, I missed a 0 here, sorry, that basically contains all the inner product between everyone. Basically, all these quantities can be expressed as a linear sum of all the inner product, a pairwise inner product between G1, G0, G1 square. It's just the inner product of G1 between itself. So yeah, basically, you can show that it's going to be linear in this matrix. And the second thing that is important to notice is that this matrix, it's a 4 here, I apologize, is a semi-definite positive if and only if there exists like such a thing that forms a grand matrix. So like basically there is an equivalence between looking for a semi-definite positive matrix and looking for this grand representation. And so now the unknown is not the x0, g0, g tilde, g1, but this like semi-definite positive matrix. And everything is linear in this matrix. So you can reformulate this problem as just this new problem, where basically the trace of this product is just like inner product between matrices. And you have like, so trace of M0 G1 is just like the thing that tries to express this quantity. And then you have all the constraints. And you have like basically the constraints that are due to like monotonicity and Lipschitzness, plus the fact that G has to be semi-definite. And so that's how we solve it. You plug this into your favorite optimizer, it solves it in like 10 seconds, actually 10 milliseconds, because it's like 4-dimensional in that case, or a bit slightly more. So you solve it, it tells you what is the hardest problem. And you just had to basically, what's a bit annoying, like you have to write yourself the matrix, you know, but it's not complicated to figure out what are like the corresponding matrix to this condition. And interestingly, you can use then basically duality. And so what's happening here? What's happening is you want to maximize your criterion given the constraint. And so basically, the constraints that will be active, so meaning that the constraint that will like reach make this an equality, are the constraints that this optimization problem is using, it's hitting to get this like max. And so in some sense, this is the constraints that are relevant, that are really the one that like makes this problem hard and like makes this max what it is. And so conceptually, this is the inequality, because this constraint corresponds to basically inequalities, like monotonicity at certain points for your algorithm. It corresponds to the inequalities you should use in your proof, because this is the one that are relevant to correspond to the max. And I can show it to you. It's just like basically a very simple convex, like linear programming duality, where basically for this specific case, for this specific formulation, the dual is basically either minus infinity or 0 if we manage to find someone, so 6 constants that corresponds to these constraints, 6 dual variables, such as the sum of the lambda mi is larger in the sense of semi-definite positiveness than m0. And like basically finding these guys gives us a proof directly, because if we find these guys, now we multiply by g and we take the trace, we know that, I forgot the sum. So this sum is negative because we use just the fact that it's constraints multiplied by a positive lambda. So this is trivial that this quantity is negative. And by the fact that like we figure out the lambda such that we have this, it means that it's smaller than this quantity. So that's it. We have shown that trace of M0G is negative, which is what we wanted. We wanted like to show that this guy was negative. So, and it generalized beyond, but like basically the dual problems gives you an upper bound on like this max that we try to maximize. So it's amazing. And it tells you, the dual variables are telling you which inequality you should combine to get this upper bound. So conceptually, it's saying, okay, my proof should just be like a combination of these inequalities. And this is exactly what we did. So like you have this new problem, this is the same, but now I just formally did it in like a more like problem, like this is the notation we would use, when we want to prove something. So we want to maximize this quantity. I'm hoping that it's 0, it's negative. You have this are the unknown, that the update rules are these ones. Like this is you in your like sketchbook, and you can use, that you can only use this inequalities. It's like monotonicity at my point, Lipschitz at all the points. And when I solve my dual problem, I have lambda 1, lambda 2, up to lambda 6 that are the dual variables that are basically telling you which inequalities are relevant for this maximization problem. I solve it for for a large quantity of L and gamma, and what we figured out is like, oh, lambda 1 is always close to 1/2, lambda 2 is always close to 2. These 3 are always close to 0, and this guy is approximately close to 3/2. And so the duality then, which is exactly like what I put here, says us exactly this in like the proof statement. This is our objective, trace of M0G, smaller than the sum of the lambda I trace of MIGI, which is just this. The sum of the inequalities that you should combine with the right coefficient to get something good. You combine this and it works. Like, so it's a bit tricky because, I will explain why it's not, I'm glorifying like how easy it is here, but roughly that's how we got the idea of combining these inequalities. And yeah, this is like, I put the proof in one slide. It's very condensed slide, but basically that's how we started the proof. Like you take like this 3, you put lambda 6 3/2, lambda 1 1/2, lambda 2 2. You get this. That's just a rewriting of the sum of the inequalities. You just expand these squares. You get like this. Trust me, it's like, yeah, it's a bit like just like algebra. You just need to use Young inequalities to say that this inner product is smaller than 1/2 of the sum of the squares. You use it here, and I think there. And basically, what you get is this, and you simplify, and that's it. You have like 3/2 of this guy. You put this one on the other side, the 1/2 on the other side, and you get the decreasing effect that you want. So I mean, this is ugly, and it would have been hard to come up, by yourself, just by looking deeply at the equations. It's hard to figure out this. Like, I'm gonna combine like basically monotonicity at xk plus 1/2 with a factor 1/2. With monotonicity at xk plus 1 and xk with factor 2, it's tricky, like it requires like decades of expert knowledge to figure out how to combine these inequalities in a meaningful way with the right coefficient. And the fact is, like, nobody managed to do it before. While, like, some of these guys are like, I mean, I don't know if they explicitly try hard, but at least, they didn't. It wasn't easy. I wouldn't say that it's, like an open conjecture that people like, really thought to find. But clearly, if these like very strong people had the solution, they would have put it somewhere. So yeah, and so what's the magic? It really tells you which inequality you should combine and like with roughly which coefficient you combine them, and it's supposed to work, and it did in that case. So yeah, we ended up with this lemma that basically says that the norm of the vector field is decreasing. And once we have this, we have one, because if you remember, we had like, the minimum iterate convergence, but since it's decreasing, the minimum is the last. That's over. So yeah, that's how we prove this. And I'm gonna do just like what we also had, like as an illustration of your point, for optimistic gradient, we had to come up with this guy that was decreasing, which is, as you can see, like relatively ugly. And PEP was very nice because we could try that like this guy alone was not decreasing, and we had to figure out what is the right coefficient there. So it really helps to iterate on this and like figure out. Yeah, so tips and tricks for like using PEP. As I mentioned, it's not a formal proof. You have to specify, but it gives like some insights. Very interestingly, and this is sad, PEP does not try to find a simple proof for you. Meaning that PEP doesn't try to put some coefficient to 0. If it's 0, you're lucky, but sometimes they are all equals to like some weird values such as like 0.2659, and you have no idea what it actually corresponds in practice. And actually, to illustrate that, there exists a proof of this result using only 2 inequalities that we missed, and that someone found afterwards. So yeah, PEP does not try to find a simple proof, but what you can do is you can conjecture which inequalities should or should not be used. You just literally like remove them in this optimization problem. You remove the inequality. So now you get an even looser upper bound. So sometimes it won't work, but if you're only keeping the inequalities that are necessary for the proof, it will. So you can play by removing some inequalities, seeing if it still works, and like then conjecturing like the stuff. So a lot of work under the hood and engineering, but it's a different approach, I would say. Yeah. So it would get, and also you can basically more generally force the dual variables to have some specific structure. You can force them to have like the value 1. You can force them to sometimes grow at a specific rate. So when you have like an inequality that depends on a specific iterate and so on. So yeah, lots of tips and tricks, but that's a very powerful tool that can be extended beyond proving like some rates for extragradient methods. I'm actually very interested if you have like any ideas on like your problems that you're working on, if you could apply this, trying to find worst case, beyond like optimization. That would be very interesting. And yeah, we also have the constraint case, which is tricky for a lot of reasons. Now you have to project back your iterates on the constraint sets, and now the norm of the operator is not anymore a convergence criteria, because when you hit the constraints, the vector field can have a non-zero value, and you can still be stuck, at the optimum. So you have to look at the residuals. The potential are more complex, but this is where like a lot of work was required. Some concurrent work proved the result for constrained extragradient that we don't have, and a result for constrained optimistic gradient that we had simultaneously. So yeah, that's the end of like kind of the story. And yeah, thank you very much. We made it. The pizza is closed. So yeah, thank you for your attention.